between 0 and b. They're all squeezed between 0 and the one before. So it can't go on forever. So there has to be a stage when the remainder is 0. So there must be some point. Maybe we'll do the second last one. Let me get my numbers right, since I'm not getting them very accurately now. If the second last one is Rn minus 3 will be and then Rn minus 2 is Qn Rn minus 1 plus Rn, and we're assuming Rn is equal to 0. So we can forget about it. And so that you have to, at some stage, reach 0 after a finite number of steps. That says Rn minus 1, the last non-zero remainder, is a divisor of Rn minus 2. Now looking back at the line above, Rn minus 1 is obviously a divisor of itself. It's a divisor of Rn minus 2, so it's a common divisor of the right-hand side. Therefore, it's a divisor of Rn minus 3. And so we can work our way up this table. It's boring to try and write out all the details, but the idea is very clear. Working back up the table, Rn minus 1, the last non-zero remainder, is a divisor of all these left-hand sides. Therefore, it is a common divisor of A and B. And where do I write now? We don't need approximations to pi any longer. So Rn minus 1 is a common divisor of A and B. Common factor, if you like, but grown-ups tend to say divisor rather than factor. But we can also approach this in a different way by taking things to the other side. So in this equation, the last equation where we got Rn minus 1, we see we can make Rn minus 1 the subject of the formula. I'm not going to write them all out. And we see Rn minus 1 is equal to Rn minus 3 minus Qn minus 1 Rn minus 2. So we see Rn minus 1, our common divisor, is expressible as a linear combination of the two previous ones. That's to say, a multiple of Rn minus 3 plus or minus a multiple of Rn minus 2. So Rn minus 1 is expressible in terms of the two previous left-hand sides in this form. And then again, we can work back up the table in this time and see that, therefore, doing this progressively, it's expressible in terms of any two successive left-hand sides. And so we get to the point that Rn minus 1 can be written in the form a multiple of A plus a multiple of B. Obviously, S and T, one of them is likely to be negative. Almost certainly going to be negative, but don't worry about that. So not everything has to be a positive integer in these expressions, but most things will be integers unless I say so. So now we have this very interesting property that we have something which is a divisor of A and B, but it's also expressed as a linear combination of A and B. Now consider any other divisor of A and B, common divisor of A and B, that's to say a divisor of both A and B, it will be a common divisor or common factor of the right-hand side, and therefore it will also be a divisor of Rn minus 1. So that means any common divisor of A and B is a divisor of Rn minus 1. And from that, you see that Rn minus 1 is the greatest common divisor, or if you like, highest common factor of A and B. And so we have now got an algorithm for, by repeated application of the Euclidean property, we get this algorithm for finding the greatest common divisor of any two integers. Now, this, you probably even, maybe even in primary school, had questions on finding the highest common factor of two numbers. And how, were you taught how to do it? Were you, no?
Yes.
Well, how would you do it? The way I've seen people do it is factorize both numbers, compare the factors, and then to see which ones they've got in common. But that's really doing it about face, in the wrong way around. Something about face. Because it is this property that the greatest common divisor can be expressed as a linear combination that leads to the fact that you've got unique factorization. You can use that to prove unique factorization. So this Euclidean algorithm finds you the greatest common divisor and also proves, is the mechanism, the basis of the proof that unique factorization is possible. And so that's a very important idea to get around. I don't know if, would you like me to do a numerical example of this?
Yes.
So, just in case I get my sums wrong, I've done it on paper beforehand, so I won't be rash enough to make up any two numbers at random, but so I decided I chose them pretty well at random. 196 and 57. And 57 is a bit short of 60, which goes, so 360 is 180, so it's 3 times 57. And, oh, I can't work them out. So I'll just cheat and look. Then the 57 comes to this side. The 25 comes to there. 25, that's easy, even I can do that in front of the board. And plus 7. Now the 25 comes here. The 7 comes there. 7 goes into 25 about 3 times. Then the 7 comes here. 4 comes here. 4 comes here. The 3 comes here. And we know immediately that the next one is going to be 0. We really wanted to. So the last non-zero remainder is 1. So the greatest common divisor of these two numbers is 1. And then you may or may not have seen that before, but the expression in the other direction is a little bit messier, but let me do that. So you wanted to get the remainders in terms of the previous one, so you start at the bottom there, but I'll right here. 1 equals 4 minus 3, which is hardly rocket science. And then we get that 4, we must substitute for the smaller one, so that's 4 minus, then we substitute for the 3, which is 7 minus 4 from the previous line. 3 is 7 minus 4, and tidy that up. That's 2 times 4 minus 7, which is still hardly rocket science. Then we must substitute for the 4, which is 25 minus 3 times 7, so it's equal to 2 times 25 minus 3 times 7 minus 7. Tidy that up. How many 25s have we got? 2 25s. Minus 6 minus 7 times 7. Even I can check that still we're still correct. Now we get rid of the 7, which is 57 minus 2 times 25.